Welcome back to our class. In this class, I'm taking guys a very important topic in CHM101. And please, this is a topic you need to know before attempting any any chemistry exam. Okay, and please stick to the end of this class because I'll be showing you guys ways to calculate questions relating to solubility products, buffer solution, as well as pH concept. Okay, so this video is very important. Okay, and a lot of questions usually comes out from this topic. Okay, now let's start with the class. Okay, now let's start with class video. Okay, now the very first part of this class is introduction to acid and base. Now there are three concepts. That describe acid and base reaction, and the very first concept is Arrhenius concept. Now this concept was given by a scientist known as Arrhenius, who defined an acid as a substance that dissolves in water to produce hydrogen ion. Okay, while he defined a base as a substance that dissolves in water to produce hydroxide ion. Then the next concept about an acid and base was given by two scientists known as Brosted and Lowry. Okay, this concept is known as Brosted and Lowry concept. Now, these scientists, they define an acid as a substance that donates proton, while a base as a substance that accepts proton. Then the last concept, which is Lewis concept, was given by a scientist known as Lewis. He defined acid as an electron pair acceptor and a base as an electron pair donor. Okay, now in our next class I will elaborate more on this aspect. Okay, I will talk about Lewis acid, Lewis base, how to know a Lewis acid, how to know a Lewis base, conjugate acid, conjugate base. Okay, now let's move to the next important part, which is pH concept. Okay, now I know that you guys have heard of the word pH. pH means power of hydrogen. Okay, yes. Now pH concept, what is the usefulness of pH concept? Now pH concept helps to measure, or rather pH helps to measure how acidic or basic a solution is. Okay, pH tells you whether a solution is very acidic, or it tells you whether a solution is very very basic. Okay, it tells you if a solution contains a weak acid, tells you if a solution contains a weak base. Okay, so that is the usefulness of pH. pH just helps to measure how acidic or basic a solution is. Now, if you look at the board very well, you find out that I give you guys four equations that you can use to calculate any question relating to pH concept. Okay, now the very first equation is pH is equal to negative log of hydrogen ion concentration. pOH, the next form equation is pOH is equal to negative log of OH hydrogen, OH concentration. Then the third formula, or the third equation, is pH plus pH is equal to 14. Then the last equation is hydrogen ion concentration then multiplied by OH concentration is equals to what? 10 raised power minus 14. So these are the equations you can use to solve questions relating to pH concept. Okay, yes. Now the formula we are going to use depends on the type of question you are asked to solve. Now let's look at this very first question. It says the pH of a solution of 0.02 molar concentration of hydrogen ion is hydrogen ion. Now look at this question very well. They're asking us to look for what? They're asking us to look for the pH, right? Yes. Don't worry about concentration. They give us the hydrogen ion concentration to be what? 0.020. Right? Yes. So which formula are we going to use? We're going to use this first one because why? This first one relates pH to what? Hydrogen ion, right? Which is very easy. Just do like this. pH is equals to negative log, then negative log base 10. Then where is the concentration of hydrogen? Concentration of hydrogen is 0.020, right? Yes, so just do it in your calculator. If we solve it on calculator, you get the answer, which is negative log of 0.020. We do it, you will get 1.69. Okay, so the pH is what? Of this first of the solution is what is 1.69. So that's to tell you that the solution is very, very acidic. Remember that I'm coming. Remember that okay, I'm coming 8, 9, 10, 11, 12, 13, 14. Okay, okay, 1, 2, 3, 4, 5, 6. Okay, 7, 8, 9, 10, 11, 12, 13, then 14. Okay. Now just remember that if the pH of the substance is 7, no, it means that the substance is neither acidic nor basic. Okay, it means that that substance is neutral. Okay, yes. Now, if the pH lies between this range from 1 to 6, know that that substance is acidic. Okay, so acidity increase in this direction. Increase acidity. Okay, acidity. Increase acidity. Right from here is increase alkalinity. Okay, alkalinity. Okay, yes. So that's to tell you that the substance that has pH of 1, so that substance is very acidic. Okay, while the substance that has pH of 6 or 5, the substance is not that acidic. Okay, yes, same goes for this side. The substance that have pH of 14 tells you that the substance is like has high alkalinity. The substance is highly basic. Okay, yes, while the substance that have a pH of 8 or 9, that substance is not that alkaline. Okay, yeah, so this is very important. Okay, now let's move to the second question, which is, now let's move to the next question. Okay, the next question, it said calculate the pH of a solution of 2.5 times 10 to the minus 3 molar concentration of hydroxide ion. Okay, now which formula are we going to use? Remember, they asked us to calculate for what? pH. So we should calculate the pH of what? Of hydroxide ion. Okay, which formula are we going to use? Now, if you look at this 4 formula I give you guys, there is no formula that relates pH. That relates pH with hydroxide ion. There's no formula here. If you look at it, this first formula relates pH with hydrogen ion. This second formula relates pOH with OH. This third, you cannot see it, cannot even see it, right? Yes. So if you look at the question, it said the pH of a solution of 2.5 times 10 to the minus 3 molar concentration of hydroxide ion. If they ask something for pH, you look at it, no formula here relates pH to OH. Now, what are we going to do? It's very easy. The very first thing we are going to do is to look for pOH first, because why? pOH is related to OH. Yes. Once we get our pOH, then we use this third formula. We put our pOH here, subtract it from 14, and get the pH. So that is just it. Okay, so what are we going to do? Let's look for the pOH first. The pOH of the solution is what? Well, according to the formula I gave you guys, pOH is equal to a negative log of base 10 of OH minus, right? Yes. Now, what is the OH? What is concentration of OH? Concentration of OH is 2.5 times 10 root power minus 3, right? Yes. So what are we going to do? pOH will be equals to what? Negative log base 10, then the concentration of OH, which is 2.5 times 10 to the minus 3. Let's do a pH. Okay, just do it like this in your calculator. Negative log, then 2.5 times 10 raised to power. Okay, 2.5 times 10 raised to power minus 3. Okay, if you do it in your calculator, minus log and 2.5 times 10 raised to power minus 3, you will get what? The pH. The pOH rather. The pOH is what? Is 2.6. Okay, so our pOH is what? 2.6. Are we done yet? No, what are we looking for? We're looking for pH, right? So we have gotten our pOH, right? We need to subtract this pOH from 14 and get our pH. So what are we going to do? It's very easy. We use the third formula, right? The third formula is what? Is pH plus pOH is equals to what? 14, right? Our pH, that's what we are looking for. Our pOH is 2.6, then 14, right? We take this 2.6 to cross it to the next side, right? Now be 14 minus 2.6. So 14 minus 2.6 will give us 11.4. Therefore, our pH is what? 11.4. Okay, so this is how to solve. This is how to solve questions when the easier to solve when they say calculate for the pH, and what you are calculating the pH for is hydrogen ion. Okay, you need to first look for the pH. Once you get the pH, you subtract it from 14, you get the pH, and vice versa. Meaning that they can ask you to calculate for the pOH of hydrogen ion. Remember, there's no formula that relates pOH with hydrogen ion. So what are you going to do? You need to first look for pH first. Then once you get your pH, subtract it from 14, you get your pOH. So that is just it. Now let's do the third question under pH concept. The third question, I said, given that the pH of seawater is 8.3, calculate the hydrogen ion concentration in seawater. It's just the reverse of this question. Okay, the reverse. In this question, they give us the pH to be 8.3, and they ask us to look for what? They ask us to look for hydrogen ion concentration, which is very easy. Okay, yes. Remember, pH is what? pH is equals to negative log base 10 of what? Hydrogen ion concentration, right? Yes. Now our pH is 8.3, right? Then they're asking us to look for what? H plus, right? Yes. So how are we going to do it? We need to take the antilog of this. We need to take the antilog of 8.3. We'll get, remember, the opposite of log is antilog, right? So we need to take the antilog of this value, which is very easy. Just go to your calculator and press shift log, then write minus 8.3. Okay, please, to take antilog, just go to your calculator, then write and then press shift and log. That will give you the antilog. Then the number, the value, you add minus. Okay, minus 8.3. So shift log minus 8.3, right? So we do it. We have what? We have 5 we have 5.01 times 10 raised to the power minus 9. So this is the hydrogen ion concentration. Okay, so this is all about pH concept. Okay, important thing is that just know the formula, and understand the question. Okay, which is very, very easy. To look for hydrogen ion concentration, take the antilog of negative of take the antilog of the number of the and negative, and then of the number, and make sure you add minus. Okay, yes. So if you want to do it, just press shift log then minus 8.3, which is very important. Okay, to give you the answer. Okay, now let's move to the next part, which is dissociation of weak acid and bases. Dissociation of weak acid and base. So let's continue with the dissociation of weak acid and weak bases. Now remember, a weak acid, these are acids that do not completely dissociate in water, whereas a base, the same thing. A weak base do not completely dissociate in water as well. Okay, so this is this dissociation of weak acid, while this is dissociation of weak base. Okay, when a weak acid dissociates partially, it gives hydrogen ion plus the negative ion, right? Yes. So examples of weak acid that not completely, of weak acid is acetic acid. Okay, acetic acid, which is also known as our common one, we commonly know it as ethanoic acid. Okay, yes. So ethanoic acid or acetic acid is an example of a weak acid. Weak acid, they not completely, yes, they don't completely dissociate in water. They don't completely dissociate into hydrogen ion. They don't completely dissociate. Example is acetic acid or ethanoic acid, which are the same thing. Okay, yes. If you look at acetic acid, which is CH3COOH. Now this acid does not completely dissociate. When it dissociates, if it gives out hydrogen plus acetate ion. Okay, yes, acetate ion. Now there is this constant that is known as dissociation constant. Okay, look at this one. You see Ka, you see Kb. Now Ka is known as dissociation dissociation constant for acid. Okay, it's known as what? For acid, it's known as Ka. Now, what does it do? Ka helps to measure the strength of an acid. Okay, yes, Ka means dissociation constant for acid. It helps to measure the strength, or yeah, it helps to measure the strength of an acid. Okay, yes. Now, the higher the Ka value, the stronger what? The stronger the acid. Okay, the stronger the acid. Okay, the higher the Ka value, the stronger the acid. The lower the Ka value, the weaker the acid. Okay, so Ka helps to measure the strength of an acid. Okay, yes, it helps to measure the strength of an acid. Now, if I want to look for the Ka of, if I want to look for the Ka is equals to what? Is equals to the concentration of the product divided by the concentration of the reactant. Okay, it is usually product up, reactant down. Okay, now if I'm to look for the Ka of ethanoic acid, how am I going to do? It's very easy. Remember, it's usually the product up and the reactant down. Okay, so Ka, since ethanoic acid is an acid, so it's what? It's Ka is equals to what is the concentration of the reactant, right? Okay, concentration of the reactant multiplying sugar. I mean, the concentration of the product rather. Okay, the product is up, the reactant is down. Okay, so the concentration of the product, okay, then divided by what? The reactant, right? CH3COOH. Okay, so this is how to look for the Ka of ethanoic acid. Okay, the product will usually be on top, the reactant usually be bottom. Okay, yes. Now about for dissociation of weak base, still the same thing. Okay, dissociation for weak base. Okay, so now in the presence of water, a weak base dissociates partially, right? Yes, into B plus, then OH minus, right? Yes, a weak base produces hydrogen ion in solution, right? And since it's a weak base, it does not completely dissociate in water. Now, to look for example of a weak base is ammonia, right? Yes, when ammonia reacts with water, it does not completely dissociate. Does not completely dissociate. Okay, it forms ammonium ion plus what gives an hydrogen ion. Okay, yes. Now Kb, what is Kb? Kb is known as dissociation constant for base. Okay, remember Ka is what? Dissociation constant for acid, while Kb will be what? Dissociation constant for base. Okay, so the dissociation constant for base is still the same thing. Okay, the product then divided by the reactant. Okay, for base still the same thing like acid, to be what? The concentration of the product divided by concentration of the reactant. Okay, now the concentration of the reactant here is what? The reactant here, I mean the product here is take the concentration. Okay, BH plus then OH minus, right? Then divided by what? Okay, this is the product, right? Then divided by the reactant, right? By the concentration of the reactant, which is B. Okay, yes. So you might ask, why didn't I put water here? For example, why didn't I put water? Because water is part of the reactant, right? Yes. Now the reason why I'm not putting water is because solid and liquid, they are not usually yeah, we don't usually use them in in expressing equilibrium constant. We don't usually use them because why? Because they have a constant concentration. Okay, so that is why it's found that I didn't add water. Okay, so in looking for the in looking for equilibrium constant, just take note that we don't make use of solid and liquid because why? Because they have constant concentration. Okay, yes. So Kb will be equals to what? The concentration of the product divided by what? Concentration of the reactant, right? Yes. Remember, if there's a liquid, for neglect the liquid, okay? Yes, we only take, yeah, we don't take the concentration we neglect liquid and solid. Okay, so if I'm to do the Kb of ammonia, how am I going to do it? It's very easy. Okay, Kb of ammonia will be equals to what? Now where is the product? When ammonia dissociates in water, what is the product? The product is the concentration of the product, right? Then multiplied by, yeah, the concentration of the two products, right? Then divided by what? The concentration of the reactant. The reactant is what? Ammonia, just ammonia. We don't involve We don't involve water or any liquid or solid in uh, in equilibrium expression. The higher the Kb, which is the higher the dissociation constant for the base, the stronger the base. Okay, the stronger the base. This is very important. The stronger the base, then the lower the Kb, the lower the weaker the base. Same goes for acid. The stronger the Ka, the stronger the acid. Okay, then the lower the higher the Ka, the stronger the acid. The lower the Ka, the weaker the acid. Okay, so that is all about. We'll make use of these things later. Okay, very very important. Now that is all about dissociation of weak acid and weak bases. Now let's move to this very very important part. Buffer solution that harbors a lot of questions. So buffer solution and then solubility product. Now let's continue with buffer solution. Okay, so where is the buffer solution? A buffer solution is a solution that maintains a nearly constant pH even when small quantities of acid or base are added. Okay, so that is a buffer solution. A buffer solution is that solution that maintain or nearly maintain a constant pH even when you add an acid or a base to that solution. That solution will still maintain that pH. I don't even understand. Now take note that a buffer solution, let's say, okay, before then, let's move to the types of buffer solution. We have acidic buffer solution as well as a basic buffer solution. Now for an acidic buffer solution contains a weak acid. Very important, okay? Contains a weak acid, and let me clear this part. Contains a weak acid and contain weak acid and its salt with a strong base. Okay, and its salt with a strong base. Now what does this mean? Now for example of this of an acidic buffer solution. Remember, an acidic buffer solution contains a weak acid and a salt and its salt with a strong base. That means that the salt of this strong acid contains a strong base. Now let me elaborate further. Okay, so let's use acetic acid for an example, which is ethanoic acid, right? Yes, ethanoic acid is a weak acid. Okay, so CH3COOH, right? Yes. Now the salt of this acid is CH3, which is sodium acetate. Okay, yes. Now an acidic buffer solution is made up of a weak acid, made up of is made up of a weak acid and its salt with a strong base. Okay, so this is the salt of this acid, of this weak acid. Okay, now if you look at this salt, remember salt contain metallic ion, right? Yes. Now if you look at this salt, this part of this whole salt is a strong base, which is CH3 COO minus. Okay, yes. Remember, normal salt is made up of positive and negative, right? Yes. So this is this is what the strong base means. I don't even understand. So an acidic buffer solution contains a weak acid and its salt with a strong base. So the salt of this weak acid usually contains what? Usually contains a strong base in it. Okay, so that is an acidic buffer solution. Okay, so the opposite will now be what? I'm coming. CH3 COONA, right? So this is the salt of the weak acid, right? Yes, just take note that I will tell you guys in our next class, though, but let me tell you guys now. Just take note that a weak acid usually have a strong conjugate base. Okay, while a weak base has a strong conjugate acid. Okay, so which is very important. Now before then, CH3COOH is a weak acid, right? Yes, the conjugate base is I think acetate, right? Yes. Now this is the conjugate base of this acid, right? This conjugate base is very strong. Okay, so that's to tell you that weak acid have strong conjugate base, then weak base has strong conjugate acid. Okay, so that is just it. So an acidic buffer contain a weak acid and its salt with a strong base is very important. Don't worry about a basic buffer. A basic buffer, just like the opposite, a basic buffer, basic buffer contains a weak base, contains a weak base and its salt with a strong acid, and its salt with a strong acid. Okay, its salt with a strong acid. Okay, yes, example of a weak base, let's use ammonia for an example, right? Yes, ammonia is an example of a weak base. Now if ammonia dissociates normally, okay, let's say ammonia reacts to water, for example, reacts to water. I'm coming. Ammonia reacts with water, it dissociates in water to form ammonium ion, right? To form ammonium ion, then plus I think OH, right? Yes. Now this is the conjugate acid of ammonia, right? Yes. Conjugate acid has, remember, a weak base. A weak base has a strong conjugate acid. Okay, so that's just it. Okay, now let's continue. Now, as a basic buffer solution contains a weak base and its salt with a strong acid. Now, let's use sodium. Let's use ammonium ion. Ammonium chloride. Yes. Now, ammonium chloride is a salt. Is a sort of ammonia, right? Yes, this is ammonium chloride, a sort of ammonia. Sodium acetate, sodium acetate is a sort of remember, different acid. Salts are formed when hydrogen ion in an acid is replaced by metallic ions, right? Yes. So this is a sort of acetic acid or ethylic acid, right? Yes. Why this is a salt? Why this is a sort of ammonia, right? Yes. Remember, I told you guys that a basic buffer contains a weak base and its salt with a strong acid in it. So this salt contains what? Ammonium ion, right? And chloride ion, right? This ammonium ion is a strong acid. Okay, very important. Okay, so in summary to everything, a buffer solution is that solution that maintains a nearly constant pH when you add an acid or a base in it. Okay, yes. Now a buffer solution is made up of, there are two types of buffer solution: acidic and basic. Now for an acidic buffer solution contains a weak acid and its salt. Then a basic buffer solution contains a weak base and its salt. So that is just it about the introduction of buffer solution. Now let's continue. Now, how does a buffer solution works? How does it work? It's very easy. Now, for example, now let's say when you had, now for a buffer solution, I told you guys that it's made up of acidic, it's made up of weak acid and its salt. For basic, made up of a weak base and its salt, right? Yes. Now, how does it work? How does a buffer solution work? When you had, remember, a buffer. Let's use acidic as an example. Let's use acidic buffer solution as an example. Specifically, these two guys, right? Now, remember, acidic buffer solution is made up of the weak acid and what, and each salt, right? Yes, and each salt. Now, how does the buffer solution work? Let's use acidic buffer solution for example. When you add an acid, when you add an acid to this buffer solution, the salt part, remember, this is a buffer solution, right? This is a buffer solution. It has a particular pH. Let's use 5 for example. A buffer solution maintains a constant pH. Even when you add an acid or you add a base, it will nearly maintains it. I don't understand. Okay, let's say the pH of this buffer solution, let's say it's 4.98. For example, this is a buffer solution now. The pH is 4.98, for example. Then we add an acid to it. We add an acid to it, right? Yes, this is how it works. The salt part of a buffer solution will react to neutralize this acid. I don't understand. To neutralize this acid, in order to, if you neutralize this acid, the pH of this buffer solution generally will still be maybe close. It will still be 4.98 or a lower, let's say 4.88. I don't understand. So that is the function of a buffer solution. Buffer solution maintains maintains a constant pH even when you add an acid or a base. Now let's say I add a base now, for example. Let's say I add a base to this buffer solution, OH, right? If I add a base to this buffer solution, the acidic part of a buffer solution will neutralize this base, enabling it to maintain this constant pH, okay? Yes, so that is the function of a buffer solution, okay? That is how it works, okay? A solution that maintains nearly constant pH. There are two types of buffer solution: acidic and basic buffer solution, okay? Yes. Now, where they usually ask you question from is measure the calculation aspect, okay? Yes, measure the calculation aspect. Now, how do we calculate the pH of a buffer solution? We are using Heisenberg equation, okay? We said that to calculate for the pH of a buffer solution, the formula we are going to use is coming. Formula we are going to use pH is equals to pKa plus log bracket open salt divided by acid, right? Yes. Now what is pK? pK is pK. To look for pK, pK is very easy. To look for pK, you need to look for a negative log of Ka. Okay, take look for a negative log of Ka. Remember, Ka is what? Ka is a dissociation constant of acid, right? Yes, so that is Ka. So look for the pKa. It's very easy to look at pKa. Take the negative log of Ka. Ka is dissociation constant of acid, and most times they'll usually give you Ka in the question. Then you take negative log of Ka to get pKa. Okay. Yes. So this is the equation used to calculate the pH of a buffer solution. Okay, so this is the equation used to calculate for the pH of buffer solution. Now let's do this. These are three questions involved. Now let's solve these questions. Okay, now let's look at it. I say a buffer solution contains 1 mole per liter each of acetic acid and sodium acetate. Okay, find the pH of the buffer solution is very easy. Okay, yes. Now the Ka for acetic acid, usually the Ka is, remember I told you guys I will give you, this is a full question, okay? Yes, the Ka for acetic acid or commonly known as ethanoic acid is, the Ka is 1.8 times 10 raised to the minus 5. Okay, yes. So they say we should look for the pH of the buffer solution that contains acetic acid and sodium acetate, right? Find the pH of the buffer solution. Now, a buffer solution contains, they say 1 mole per liter each of acetic acid and sodium acetate. So it's very easy. Okay, just go to here, you say pH. Let's look for the pKa first, okay? Yes, remember pKa is what? Is equals to negative log base 10 of what? Of the Ka, right? Or you can also negative log of Ka, right? Yes. So Ka is what? Is 1.8 times 10 raised to the power minus 5, right? So just go to your calculator. Go to your calculator, then look for the negative log of this value. Just go to your calculator, press negative minus log 1.8 times 10 raised to the power minus 5. Okay, so if you take it, you have 4.744. So the pK is equal to what? 4.744. Okay, so we are going our pK to be what? 4.744, right? So I'll put it here like this: 4.744, then plus log bracket open. Now look at the question. Now, normally we use concentration of the salt divided by the concentration of the acid. Okay, yes, we use the concentration of the concentration of the salt divided by the concentration of the acid. Then we divide it, then we take the log. Very easy. Okay, but I majorly use mole. Okay, yes, let's just use mole. That would be easy for us. Okay, so we use mole. Remember, you can use concentration of the salt, then concentration of the acid, to look for the pH. But you can still use mole. I will advise you use mole. Okay, so if you look at the question, it said the buffer solution contains 1 mole per liter each of this is the acid, right? This is the acid and this is the salt, right? So it said it contains 1 mole per liter of the acid and 1 mole per liter of the salt, right? So what that you guys, I'm using mole, right? So what is the mole of the salt? This is the salt, right? They say 1 mole per liter each. So the mole of the salt is 1, right? Is 1. Then what about the acid? The mole of the acid is still what? Is still 1, right? Yes. The mole of the acid is still 1, right? Yes. 1 divided 1 will still give us 1. Now the log of 1, log 1 is what? Log of 1 is what? 0, right? Yes. So the log of 1 is 0. So 4.744 plus 0 will give us 4.744. So this is the pH of this buffer solution here. So it's very easy, okay? Yes, the more we go, the more it gets trickier. Okay, so they'll give you the Ka. When you look at a pK, it's very easy. The pK is negative log of Ka value. Yes, then use the mole of the salt divided by the mole of the acid. Use mole. Very important, okay? So the pH of this buffer solution is 4.744. Okay, now let's do the next question, okay? Yes, so it's still a continuation, okay? Now, what is the pH if 0.2 mole hydrochloric acid is added to 1 liter of the buffer? This is very important, okay? Yes, they say what is the pH if you add 0.2 mole of acid? Now, I told you guys earlier that how a buffer solution works, right? Yes, I told you guys that for an acidic buffer solution, for example, when you add, or generally a buffer solution, when you add an acid to a buffer solution, or an acidic rather now, when you add an acid to an acidic buffer solution, the salt side, the salt part will neutralize the acid, the hydrogen ion, the acid you added, right? Yes. Okay, let me just explain it again. This is weak acid plus the salt, right? So this is a buffer solution. This is a buffer solution. Okay, buffer solution. Now, when you add an acid to an acidic buffer solution, the salt part of this buffer solution will neutralize this acid. They will neutralize the hydrogen plus. I don't even understand. Yes. So if you add a base to it, OH, the weak acid part of a buffer solution will neutralize the OH. So that is it. So now if you look at this question, they say what is the pH if 0.2 mole hydrochloric acid is added to 1 liter of the buffer. Okay, let's say this is the buffer now. Let's say, okay, this is buffer. We added 0.2 mole of HCl to it. What will happen? Now remember, I told you guys, when an acid is added to an acidic buffer, it will be what? It will be the salt that will neutralize the acid, right? Yes. Now, previously, don't forget that. Okay, that is just it. Okay, so okay. Now, don't forget that we are still, it's still a continuation of the question we are doing. Oh. Yes, our pK here we got that time was 4.744, right? Yes, plus log. Now, I told you guys we use more of the salt, right? Yes, the salt, more of the salt. The more of the salt earlier was 1, right? Yes. Then more of the acid earlier was still 1, right? Yes. Now, but if you look at this second question, they told us that they had 0.2 mole of hydrochloric acid to the buffer, right? Yes. So therefore, this salt, the salt part of the buffer solution, will neutralize the H plus, right? We neutralize this acid, right? And remember, the salt part has a minimum 1 mole, right? Yes. So it will not be 1 minus 0.2 because why? Because the salt part is one that usually neutralize the acid added, right? Then the acidic part also has what? More of 1, right? Yes. Now if you add acid to acid, what will happen? So the acidity will increase, right? So 1 plus what 0.2. I don't know if you understand. So when we add 0.2 mole of hydrochloric acid to this buffer solution, remember this buffer solution has 1 mole of salt, 1 mole of acid, right? 1 mole of the salt, 1 mole of the weak acid, right? Yes. So the salt will neutralize the acid, right? So that is why you see minus, there is minus 0.2. Neutralize 0.2 mole of the acid. Then this same 0.2 mole of the acid will be added to the weak acid. So that's why you see plus here. So that is just it. Okay. So everything here will now be minus 0.2, then plus 0.2. Okay. Yes. So that is just like adding we add acid to this to an acidic buffer solution. The mole of that acid we add to the acid part, we add the salt part of the buffer solution, we neutralize 0.2 mole of that acid, right? So that's why I see minus, that's why I see plus here. Okay, so 1 minus 0.2, 1 minus 0.2 give us 0.8. Okay, give us 0.8. So everything here will be what 0.8, right? Yes. Then 1 plus 0.2 give us what 1.2, right? Yes. So if we divide it, 0.8 divide 1.2, 0.8 divide 1.2, we get we have 0.667. Okay, so 4.744 plus log everything here is what 0.667, right? Yes. So the log of 0.667 is minus 0.175. Okay, so minus 0.175, right? Yes. So everything here is what minus 0.175, right? Then we add this one to it, 4.744 plus, right? Plus and minus will give us minus, right? So we subtract it. So 4.744 minus 0.175. 4.744 minus 0.175 will give us 4.569. So the pH of the buffer solution is 4.569, right? Yes, 4.569. So that is the pH. Okay, yes, it's very easy. When now this part here, for example, this part, now generally if they just say they ask you to calculate for the pH of the buffer solution, look for the pKa. I will taught you guys how to look for pKa. Then plus, now if you look at the question, they give you the more of the salt, they give you the more of the acid. Use the moles, divide it, then take the log of the answer you get, then add it to the pK, you get your answer. Now to make it more tricky, they will ask you, they will say, okay, when an acid is added to the buffer, calculate the pH. Now when an acid is added to a buffer and they ask you to calculate the pH, look for the pK first, then remember when you add acid to a buffer solution, the salt part neutralizes the acid, right? Yes. So when they add an acid to it, just let's say they say 1 mole of acid to the buffer solution. Yes. So you subtract 1. Let's say the mole of the salt generally was 5, and they said they had 2 mole of acid to the buffer solution. Just subtract 2 from 5. Then for the acidic part, let's say the acid, let's say it's 3, you add 2 to it. So that is how it is. So that you'll not be 3, you'll not be 5. So that is how it is. Okay. So it's very, very easy. Same goes for base. When they add base to the buffer solution, when they add base to the buffer solution, let's say they add 2 mole of so let's say the base is 2 mole. The salt part, you add it. Then for the acid part, let's say the acid part is 3, you subtract it. So it's opposite. Okay, so that's just it. Now let's do the next question. They said, okay, so let's do the next question. It's very easy. The more we do question, the more you understand it better. Okay, so now look at the next question. It said, how many moles of sodium acetate must be added to 1 liter of 0.5 molar concentration of ethanoic acid solution to make a buffer of pH 5? Okay, you will know that Ka is of ethanoic acid is 1.8 times 10 raised by minus 5. Okay, so let me explain the question. Remember, to look for a pH of a buffer solution is pH equals to pKa, right? Then plus log salt over acid. Remember, you use the mole of the salt and the acid, right? Yes. Now if you look at, they say how many moles of sodium acetate? Sodium acetate. Remember, I told you guys, sodium acetate. This is sodium acetate here, which is the salt of the acid, right? The acid is what? Acetic acid or ethanoic acid, right? So this is the salt, which is known as the salt. This is salt. This is the weak acid. This is the salt. Remember, a buffer solution is made up of an acidic buffer solution is made up of a weak acid and its salt, right? Yeah. So this is the salt. This is the weak acid. So they say how many moles of the sodium acetate, which is this salt. Now we are looking for the mole in this question. We are looking for what? The mole. We don't know. Okay, we don't know the mole. Okay, how many moles of sodium acetate must be added to 1 liter of 0.2 molar concentration, to 1 liter of 0.2 molar ethanoic acid solution or acetic solution. Now, if you look at this part, this part here, this is 1 liter, this is molarity, molarity, or you can call it concentration. This is 1 liter, which is volume, while this is what? This is molarity, right? Yes. Look, and remember, I told you guys that we make use of mole. Let's not use mole. Let's not use concentration, right? Yes. So we need to look for the mole, which is very easy. Remember, mole is equals to molarity or C or concentration times volume, right? Yes. So we want to look for the mole of the acid, which is very easy. The concentration of the acid is what? 0.2. Then times the mole. The volume of the acid is what? Is 1, right? Is 1. So therefore the mole is what? 0.2. Okay? Yes. So the mole is 0.2. Therefore, the acid has a mole of 0.2, right? The salt part of the acid is, we don't know the mole. That's what they told us to look for, right? Yes. Now what about the pKa? The pKa is easy to look for. pKa is what? Is negative log of what? Of the Ka, right? Negative log of the Ka. So the negative log. Now where is the K? Where is the Ka? In the question, the K is what? Is 1.8 times 10 to the minus 5. So 1.8 times 10 to the minus 5, right? So if you do it in your calculator, negative log of 1.8 times 10 to the minus 5, you have 4.744, right? So our pK is what? 4.744. Okay, 4.744. Then plus log. Okay, the source we don't know the. That's what we're looking for. That is we are looking for the mole. We don't know the mole. Then for the acid, the mole is what? 0.2. How do we got the mole? Remember, molarity is equals to number of mole of solute over what? Volume of the solution, right? Yes. The molarity they gave us was 0.2. Then the volume is 1 liter. So if cross multiply, 0.2 give us 0.2 times 1 give us 0.2. So the mole of the acid is 0.2. We are looking for the mole of the base. Now, of the salt, rather than the pH. Look at it. Say, how many moles of sodium acetate must be added to 1 liter of 0.2 molar concentration of acetic? Okay, must be added to 1 liter of 0.2 molar acetic solution. Okay, acetic acid solution to make a buffer of what? Of pH 5. So the pH of the buffer solution is 5. So I'm looking for N, which is we're looking for number of mole of the salt, which is very easy. Okay, so this one comes over here. 5 minus 4.744, which is equals to log N over 0.2, right? Yes. So 5. Let's do that. 5 minus 4.744. If we do it, we get 0.256. 0.256. Okay. Yes. Don't forget about the log N over 0.2, right? Yes. Remember, to look for and to want to remove this log, right? So we'll take the anti-log of both sides. So we take the anti-log. Take this. Okay, I'm coming. Now, if we take the anti-log of I'm coming. Okay, so let's take the anti-log. To cancel this log, we take the anti-log, right? Yes, of both sides. So to cancel log, we take the anti-log of both sides. So if we take the anti-log of this value, we have something like this. Remember to take anti-log, just press shift, then log, then write the value. Okay, since there's no minus here, just write the value like that. Okay, yes. Unlike in pH, where if there's a negative value and you are to look for the anti-log, you take the anti-log of your anti-log, then minus, write your number. Okay, since there's no minus here, just press the anti-log and put your value. Anti-log. To look on the anti-log, just press shift then log. Okay, then write your value 0.256. Okay, so when I do it, I got 1.8. 1.80. Okay, 1.80 to let's just use 1.8. So the anti-log of everything, because anti-log, if you take the anti-log of both sides, log will cancel, the anti-log cancel the log, then take the anti-log will cancel the log here, right? Then we'll take the anti-log of this side, right? Yeah, so the anti-log of 0.256 is 1.8. So now we now left something like this. 1.8 is equals to n divided by 0.2. Okay, yes, remember to remove log, we take anti-log of both sides. The anti-log here will cancel the log. If we cross multiply 1.8 times 0.2, we give us 0.36. So 0.36 is the mole of the salt. Okay, yes. Now let's move to these other questions 2 and question 3. For question 2, they said a buffer solution was obtained by adding 8.3 gram of acetic acid, 16 gram of sodium acetate. Okay, solution of 0.07 ml of 1 molar concentration of hydrochloric acid is added to it. The dissociation constant of acetic acid, which is Ka, is equals to 1.8 times 10 to the minus 5. Molar mass of acetic acid and sodium acetate are 60 and 2 respectively. So what are they telling us to look for? We are looking for the pH of the buffer solution. Okay, remember to look at the pH of the buffer solution, pH is equals to pKa, right? Then plus log bracket open the salt, the mole of the salt divided by the mole of the acid, right? Yes. So now if you look at it very well, they give us Ka, right? The Ka to be 1.8 times 10 to the minus 5. So let's look for pKa first before we look for this other one. Okay, the pK, remember pK is equal to a negative log of Ka, right? Yes, so negative log, the Ka is what? 1.8 times 10 to the minus 5, right? So let's look for negative log. So minus log 1.8 times 10 raised to power minus 5. Okay, so 10 raised to power minus 5. So our pKa is 4.744. Okay, so our pK is what? Is 4.744, right? So our pK is 4.744. So let's put it here. pKa 4.744, then plus log. Remember, I tell you guys that we make use of, let's use mole so that you can easily get our answer. Make use of mole, the mole of the salt divided by the mole of the acid, right? Yes. Now the salt, the weak acid is what? Is acetic acid, right? Which is known as acetic acid, which is known as ethanoic acid, right? Then while the salt is sodium acetate, which is CH3, COO, and Na sodium, right? So this is the weak acid, this is the salt of the weak acid. So all of them comprises the buffer solution, right? Yes. So this place is for the mole of the salt over the mole of the acid, right? Now if you look at this question very well, they said okay, let's go for the mole. Let's go for the mole of the acid, of the salt, and the mole of the acid first. Okay, so a buffer solution was obtained by adding 8.3 gram of acetic acid. Remember, number of mole is equals to given mass, right? Given mass over what? Molar mass, right? Given mass over molar mass, right? So the given mass of acetic acid is 8.3. Okay, we want to look for the mole of of the acid, 8.3. Then the molar mass, I said the molar mass of acetic acid is 60. Okay, so if we divide it, 8.3, 8.3 divided 60 will give us 0.138, 0.1383. Okay, so this is the mole of the acid. Okay, the mole of the acid is 0.1383. Okay, then what about the mole of the salt? The mole of the salt is 16 gram. So the given mass of the salt is 16. Then of course the molar mass of acetic acid and sodium acetate. So the molar mass of sodium acetate is 82. Okay, 82. So if we divide it, 16 divide 82 will give us 16 divide 82 give us 0.195. Okay, so 0.195, 0.195. Okay, so this is the mole of the salt, which is 0.195. Okay, are we done yet? We are not done yet. If you look at the question very well, they said okay, solution of 0.07 ml of 1 molar concentration of hydrochloric acid is added. What are they telling us? They said that they had acid to the buffer solution. So what are we going to do? Since they had acid to the buffer solution, right? Yes, if you look at the question very well, it says solution of 0.07 ml. This is volume of 1 molar concentration. This is molarity, or you can simply say concentration, right? So we want to use these two, volume and molarity, to look for the mole of hydrochloric acid. Remember? Yes, right, yes. So molarity, we all know molarity equals number of moles of solute divided by the volume of the solution, right? Yes, so we're looking for N. So if we cross multiply, N is equals to what? Molarity times volume, or you can also say C times V. They are the same thing. Okay, so molarity times volume. The molarity of the acid is what? Is 1. Okay, then the volume is what? 0.07. 0.07. Now since it is in mil, we need to convert it to liter by dividing by what? 1000, right? So we do everything. 1 times 0.07 give us 0.07. So 0.07 divided by 1000 to give us 5 times 10 to minus. 7 times 10 to minus 5. So therefore, our number of mole is 7 times 10 to minus 5, which is something as 0.00007 mole of hydrochloric acid. Now let's go back again. Okay, so we have looked for the mole of this. This is more of the salt, this is more of the acid, right? Now this is the mole of the hydrochloric acid that was added to the buffer solution, right? So hydrochloric acid. Now when 0.00007 mole of hydrochloric acid is added to this buffer solution, what will happen? It is the salt part that will neutralize the acid, right? Yes. Since it is the salt part that will neutralize the acid, to put minus here, right? Minus 0.0. Okay, I'm coming. 0.1. Okay, so 0.1 0.195, right? So when we subtract it from what? We subtract, right? I've told you guys earlier, subtract 0.00007, right? Then divided by, I'm coming, 0.1385. Okay, so since we are adding acid to the buffer solution, the salt part will neutralize the buffer solution, so that's why it's minus. Then for the acidic part, since we're adding acid plus acid, so the acid will increase, right? The acid will increase. So here will be plus 0.00007. Okay, yes. So let's do it. I'm coming. Okay, so I'm coming. Okay, so now let's do it. we subtract this one now, 0.195 minus 0.0007. Okay, so remember I told you guys that when adding a acid to the buffer solution, the mole of the acid you subtract it from the salt, then the mole of the acid again you add it to what? To the acid. I don't know if you understand. This mole, so since you're adding acid to the buffer solution, you subtract that mole of acid that you're adding to the buffer solution, subtract it from the from the mole of the salt. Then also, since you're adding acid, you add the mole of that hydrochloric acid to what? To this acid. So that is just it. Okay, so if subtract, we have something like this. We have subtractive, we have 0.19493, then divided by, now we add the two this thing, we add the two mole. Okay, so 0.1385 plus 0.00007. If we do it, we get 0.13857. Okay, so let's divide it. Okay, so let's divide it. I'm coming. So okay, let me just do it straight, or let us divide it first. Okay, so 0.19493 divided by 0.13857. If you do it, you get 1.4. So we have 1.4 here. Then we look at the log. So the log of 1.4. Log 1.4 is 0.146. Okay, so yes, let me see. Let me do it again. I'm coming. Let's divide it. So 0.19493 divided by 0.13857. Okay, so we have 1.406. Okay, 1.406. 1.406. So the log of 1.406, log of 1.406 will give us 0.147. Okay, then plus 4.74. Okay, so plus 4.74, if we add it, we get 4.744, right? Okay, plus 4.744. Okay, so if we add this, we have 4.891 as the pH. Okay, so this is the pH of the buffer solution when 0.0007 mole of acid is added to it.